part C.3, prove Fibonacci formula. In this video, we will complete the main step of the mathematical induction to prove the Fibonacci formula. We have completed the base cases verification, that part. Yeah. Now we need to, work on the remaining part. All right. First, let's look at our goal. We need to prove this formula. All right. And we want to take mathematical induction. Yeah. Based on the mathematical induction, 3 steps, right? First step, base cases. Yeah. Sometimes more than one base case. So base cases verification. We completed. Yeah. Second step, induction assumption. We need to make induction assumption. All right. Let's look at that. So what is the induction assumption? All right. Pretty much standard. Yeah. We assume that the formula is true for the subscript in the range. Yeah. We need to pay attention to the range. Okay. So this formula is true when the subscript falls into this range. Greater or equal to 2, less than or equal to n. That's assumption. All right. Then the goal. After that, step 3, we need to verify that f sub n plus 1 equals the formula with a similar form, but we need to replace the exponent by n plus 1. That n plus 1 is out of the range. Okay, yeah. N plus 1 is out of the range. But we can still prove it is true, right? Yep, we will do it. Yeah, we will do a lot of work to prove it is true. Yeah. You can see after we prove it is true, actually we extend the range, right? Yeah, the range, we prove n plus 1 also true. Okay, that means we can make the range larger, extend the range, n plus 1 included in the range, right? Then, because we prove when you use the largest number in the range, your plus 1 still true, right? So you can keep extending the range bigger, bigger, bigger. Eventually, our range covers all the integer k. Integer k, all the integer k. We can cover it. All right, so that's the, why mathematical induction, this powerful tool works. That's the logic. All right, so let's do the work here. Formula transformation. When we need to prove this formula, yeah, all right, let us start from our recurrence relation. Yeah, this is our recurrence relation. Yeah, so it must be true. All right, yeah. Then, because fn minus 1, both subscripts, they fall into the range, right? Both subscripts fall into the range, so we can apply induction assumption on these 2 terms. So we just plug in. So we have the first fn expression, this one. The second fn minus 1 expression, the second one. Yeah. All right. It must be true Then we go to the next step. We try to combine the terms, make it look a little better. Yeah. So we have this expression. Yeah. Now let's examine the expression. What property we can observe here? The key property we can observe here. Yeah. Here you can see we change the order of the terms. Yeah. So we put the power of phi terms first, then fraction forms next. Yeah. Basically two parts. All right. Yeah. The non-fraction part. So look at the non-fraction part and the fractional part. They should be quite different, right? Yeah. But when we look at the non-fractional part, should we compare it with the non-fractional part of our goal representation? Yeah. When we look at the fractional part, should we compare that part with the fractional part of our goal representation? Right? So by the natural understanding, they should be connected, right? Yes. So we need to, at this point, we need to use some, imagination or some assumption. Yeah. Guess and verify, right? Yeah. We need, at some points, we need to make some reasonable guesses. Then we verify. Yeah. Here, we do that. Yeah. We feel we should have things like that. We make our guesses. We should have things like this. Yeah. Phi to the n plus 1 should be equal to sum of these two power of phi with lower exponents. Yeah. The first guess. All right. Second guess, the fractional part. If we can show these two equalities are true, then we're done. Then we get our goal expression. Yeah, we're done. Yeah. But we make reasonable guesses first. Then it will be much easier. Yeah. So this step is important. Yeah. Let us go to the next step. Yeah. All right. So the first guess, this one, pretty easy to verify. Yeah. This one, we can see it immediately. Yeah. So what's that? We start with one of the properties of golden ratio. Phi squared equals phi plus 1. Right? Yeah. One of the two properties. Remember? Yeah. From there, then we multiply the equality, both sides, by this term, phi to the n minus 1th power. Now, after that, we get exactly our first guess is. Okay, yeah, so we have it. Pretty easy. Yeah, we're done for the first guess. Yeah. Next, the second guess. Second guess because it takes the fractional form. It is a little harder than the first one, but not too much harder. So we can handle it. Yeah. So let us work on it. Yeah. So this is our goal. Our goal, we want to prove this equality, right? So we put our goal here. In order to achieve this goal, what should we do, right? So here we use another commonly used thinking. So that is the backward thinking. Yeah. So that's pretty common. Yeah. Many problem solvers like to use this kind of thinking, backward thinking. Yeah. Here, let us use it. Yeah. All right, so the backward thinking, if this equality is true, what can we get? Right? So we do deductions backward. Yeah. So we multiply. We like to eliminate the denominators. So we multiply what? Yeah, the common denominator, right? So the common denominator, this is the common denominator, right, of all the terms. Yeah. So we multiply that. Yeah. So after simplification, we have this equality to be proved. Yeah. But we know these two, they are equivalent. These two, they are equivalent. So the arrow, both directions we can go equivalent. All right. But this one still, this current one still containing power of -1. Still annoying. Yeah. Not quite match what we can see, obviously. Yeah. So we like to tackle that part, -1, power of -1, that part. Okay, we want to remove that part. All right, how to remove that part? Now, we multiply that equality to be proved both sides by another special power of -1. Okay, so this power of -1, both sides of the above equality to be proved. All right. After simplification, what will we get? Right? What will we get? 1 equals phi squared minus phi. Yeah. 1 equals, right? Yeah, let me double check. Yeah, correct, right? Although we changed the order a little bit. It's correct, okay? Phi squared minus phi. Is this true? If you compare this equality to be proved with our second probability of golden ratio, we just compare with it. Yeah. Second one, exactly the same, right? The second one, exactly the same. Yeah. So we can check it, confirm it is true with a lot of confidence, right? A lot of confidence. We're 100% sure this last equality is correct. Okay? Then we go backward direction, but for the previous deduction chain. Yeah. Yeah. All right. Yeah. Or forward, backward, with respect to something, right? Yeah. All right. So then above one must be true. Yeah. So we check it. Yeah. The previous one must be true. We check it. Yeah. Then another previous one must be true. We check it. Yeah. That means the our fractional expression, our guess, second guess, also must be true. So we're done. All right. So we complete the proof. The third step of mathematical induction. So we're done. Yeah. All right. So we complete video part C.3. Yeah. Our last one. C.4, we will find the formula. Yeah. C.3, and including C.2, we verify the formula. That's different from finding the formula. So our last video, we will find the formula directly. All right, so let's stop right here.